Let's consider a current carrying wire that has been bent into a circular shape. So this is a loop that carries a current I. There's a current flowing in this circular loop like that. And we can use the Biot-Savart law to work out what is the magnetic field produced by this wire. So you use the right-hand rule, thumb points in the direction of the current, and you can see that there's magnetic field lines coming out of the loop and then circulating around. So you can draw those magnetic field lines, and they look something like this. And on the other side, a few more. And if you look at the direction of the magnetic field, the fields are pointing in this direction. Now it's an interesting aspect of these field lines. When you look at them, you might consider drawing a little container around the current carrying loop, and imagine that you wouldn't see inside of the container what's inside of there. If you're only looking at these field lines, you might actually think that there's a bar magnet at the north pole and a south pole like this. So you wouldn't be able to tell by looking at the field lines whether the source of those magnetic fields is actually a current loop or a permanent magnet. So that's some food for thought there. Quantitatively, how you can find those magnetic field lines, one of the Maxwell's equations is called the Ampere's law, which states that the magnetic field vector taken dot product with the line element dl, and we do a closed path, must be equal to mu naught times the current enclosed. So let's consider a current that flows along this path here. There's a current flowing upwards along this wire, and we can consider an Amperian loop. The Amperian loop can be of any shape. It loops around the wire like that, and the orientation of the handedness is such that a positive current that goes in the direction of the thumb, and the fingers are pointing in the direction of the path. So the path, the Amperian loop, has got directionality. So dl is a line element vector in the direction that we are traversing the path, and it has to be closed. That's what the circle there reminds us of. And b is the magnetic field vector, and the dot product here tells you that at every point you're taking dot product between the magnetic field and the line element as you're traveling around the loop. And the statement is that whatever this line integral turns out to be, it has to be equal to constant times the total current enclosed by the loop. And by total current, what we mean is we sum up all the current flows in the positive direction, and we subtract all of those currents that are flowing in the opposite direction. So this would be a minus current, that's a plus current. You sum up all of them. In this case, the enclosed current would be 0 because there's equal amount of positive and negative current flowing through the loop. And this is very similar to the Gauss's law, where we were calculating how much total net charge is enclosed in some three-dimensional volume enclosed by a surface. So it turns out that if you've got a perfect cylindrical symmetry, for example, in the case of a straight current carrying wire, we know that the magnetic field lines look like circles around the loop, and in this case we can actually calculate this explicitly, and we obtain the dot product gives you just the magnitude of the magnetic field multiplied by the length of the path that we are traversing in the circular case equals mu naught times I, and therefore we obtain that the magnetic field equals mu naught times I divided by the length, and in the case of circles it would be 2 pi times the radius of the of the circle. And this is the formula you have already encountered last week.